Myself, Jijendra. Subject name is Design of Machine Element. In this, my topic is about in-wheel motor roll again. Introduction. Need for more environmentally friendly and less fossil fuel dependent transport is the top priority expressed in strategic document of European commissions and other leading global institutions, including the Chinese government and United Nations. With the success of Tesla, Nissan Leaf, BMW, and other popular fully electrical vehicle, the public opinion on EV vehicles increasingly positive, and there is strong market pull. The EV market is growing by over 40% annually, and the total number of batteries in electric vehicles on global roads expected to reach 20 millions by 2020. And additional technologies push to promote the widespread use of electric drives in a notable range of applications is required. The demand or radical new solutions in passengers car electric propulsion system represents tremendous potential and requires a clean approach, a new start with a new of thinking opportunities to make electrical vehicles more energy and cost efficient. After more than a century of internal combustion engine uh, dominance in the field of passengers cars and other vehicles, the central motor driver trains architecture with mechanical transmissions is optimized to the extent where innovation process are significantly declarated to ongoing transitions to hybrid and electrical propulsions is bringing some fresh ideas and advantages, but due to low travel range and weight of batteries, new solutions are required. Having two different propulsion system is not as efficient as having only one, so the trend is to eliminate the ice in the long run. The rapidly evolving electrical vehicle market, central electric motor drivetrain, and dominant in today's vehicle in compared to disruptive in wheel motor direct drive propulsion. A central electric motor drivetrain has several disadvantages, introducing a large modern in wheel electric motor in a green color is explored view with tire rim and disc brake. This is the diagram of modern wheel in electric motor. The green color is an explored view of tire rim and disc brake. Mechanical assemblies such as in wheel motor are a perfect example of product that requires multidisciplinary optimization, since several demanding requirements need to be envisioned before prototypes can be made. The necessity for a high torque, low mass, and sufficient stiffness is vital for achieving good vehicle performance in relation to reliable operation without deteriorated properties in challenging environment. To maintain an in-wheel motor performance, mechanical development requires optimal design correlating the housing and bearing stiffness matrix and elastic deformation related to internal thermal and stochastic external mechanical loads. Controlling dimension clearance between on rotor glued magnets and stator windings is of key importance to meet motor functional, that is the rotation, and maintain operation throughout its operation. influential mechanism to motor performance. Mechanical origin analyzed permanent magnetic scenarios. Yes, in wheel motors are electromagnetically designed with a nominal air gap between stator lamination and on rotor glued magnetic normal dimensioned to 1 mm. The physical air gap is essential for ensuring the first mechanical function of every rotational device, rotation of part relative to another. As in wheel motors are exposed to several impacts which can be determinantal to its functionality. A preliminary unique review of mechanical failure modes has been made in concluding remarks over a failure mode and effects analysis of all potential mechanical failure modes and causes within assigned individual risk priorities number based on obtained lecture. The most wide cited challenges seems to manageable and have been already solved within the initial development phases. These includes potential determinants driving dynamic due to higher masses and sealing issues due to the combinations of air gaps diameter and required low seal rotation resistance. Unlike the presumably known failure modes causes material properties, in order to accurately characterize a motor's performance via air gap conservation structural, mechanical and thermomechanical FEM analysis was also performed and later verified the experiments. For this purpose, the basic material properties of an individual part should be exact. This section covers the material's mechanical properties, including elastic modulus, Poisson ratios of deformations, and heat expansions for all influential parts, including composite assemblies such as laminated blade, back, and winding, where additional measurements had to be made. Winding assemblies, explosive resins and copper windings are inserted blade lamination slots with a fill factors of 49% and have much lower values of elastic modules than steels. Consequently, they do not decisively impact on the assembled stiffness and can be neglected. The epoxy resin has elastic modulus of 7.5 and 8.7.5 to 8.5 gigapascals, and copper wire 120 gigapascals, while steel has 210 gigapascals. In the addition, the heat expansion coefficient was measured for the used composite element. The composite material was dismounted from the starter housing, heated up to the different temperature and measured several times using the um, measure value of average heat expanded dimension. The heat expansion coefficient for the winding assemblies was calculated to alpha is equal to 13.1 to 10 6 by kilo, which is equal to steel's heat expansion coefficient. This is the diagram about blade pack plus wind disassembled for the starter housing aluminum alloy part. The main motor aluminum alloy part is shown in this figure, decisively contribute to motor performance via stiffness, cooling ability and emissions. Material parameters are of major importance for all structural modeling within the development process and later the design optimizations of prototype. Material testing was performed using standard tensile specimens, including several static tension tests and extensive cycling testing, which will not static tension which will not be presented within this paper due to the space elimination. Static tensions were performed in their different institutions and on three different testing benches. Each specimen has been heat treated according to T6 solution for 6 hours under 540 degrees centigrade and artificially aged at 155 degrees for additional 4 hours. Now, this is the graph which indicates the tension test of cast aluminum alloy specimens with RM in Newton per mm square. It indicates about stress and strain relationship, and we can see there is a slightly increase in graph it and the bend at failure. While the material will be failuring state, there will be the bend occurs. Experimental part, in the order to define the maximum deflection angle of standard hub bearing, a test set for moment applications and angle measurements was designed. A schematic presentation is shown, while the complete measurement report has been added as a supplementary report to this article based on the viewed obtainable lectures on hub bearings deflection angle. An angle between 0.25 and 0.6 degrees is expected for movements up to 600 mm, 32, 33, 34, 35, 36 and 37. A dedicated to tool was designed that induce only the moment load to hub bearing unit. With this approach, credible measurements has been obtained and verified with dedicated analytical software uh, for double row angular contact ball bearing. The measurement have been performed and linear trend line approximation of the function obtained from the test was made. This is the diagram which shows the hub bearing in the section cut with the deflection measurements. Schematically it was shown. The alpha faces indicate the deflection angle of rotating part to static part, and the middle of the part is the rotating part loaded with momentum. M is indicates the momentum and the static part. Results of housing and hub bearing deformation simulation. Individual simulations of loads applied to the in wheel motor assembly has been performed, and worst case elastic deformation has been observed via FEM analysis. Maximum axial acceleration based on 30 has been applied to the motor assembly, and individually maximum radial acceleration 365 meter per seconds square based on 40 was applied to the motor assemble. And finally also the maximum centrifugal force at 1200 rpm. Visualizations of simulated deflections in an ex- exaggerated state is shown in the figure, and it is a used condition. The figure ABC, which was indicates a worst case housing displacements. A, it is a radial, B is a axial, C is centrifugal force including related deflection phases. The diagram which shows the radial, axial and centrifugal forces in the worst case of house displacement. Conclusion: the normal size of the physical air gap is dimension to be 1 mm, and reducing its size by 0.5 mm, for example, would result in higher density of magnetic flux. However, it could also induce potential interference between stator and rotor parts when operating. The torque again would be only 10% of nominal continuous torque, while the probability of interface would increase greatly. For this reason, the mechanical design is aimed to nominal value 1 mm and deviation smaller than 20%, which are arbitrarily defined as optimization objectives in order to characterize mechanical loads, thermomechanical load, and design assembly yield to motor performance. Direct measurement inside the air is needed. A Hall effect measuring system measured the oscillating magnetic flux inside the air gap was developed and presented in research. This method was used to validate analytical tolerance, stack analysis, and IWM assembly stiffness. Thank you.